All right, so let's get started. Just a reminder that there is the project contribution is posted. If some of you maybe forgot about this or whatever, project contribution is due. Oh my goodness, that's sooner than I thought. Even next Friday is your last day to submit a project contribution if you want to take advantage of that application objective. The project contribution I did since the last time I talked about this during a lecture. I added a video. This is my video from last semester where I walk through the entire process of the project contribution. I even do a demo of creating a pull request, cloning forking a repo, cloning it, committing, pushing to it, and then creating the pull request back to the original project. So if you were waiting for me to do that, this has been here for a while. I just didn't announce it during a lecture. It's a little bit hidden. And when you finish your project contribution, there's this form here to let me know that you finished it. Some of you created pull requests but never filled out this form. So if you're looking for credit for those and you want me to review them, check that out. Fill out that form and let me know. But this is a thing. This is an application objective just sitting there waiting for y'all to finish it. So far, I have a total of 0 students who have filled out that form. So I just want to put out a reminder, make sure everybody's aware that exists and that's coming up. I get it if most of you are busy with genetic algorithm and everything. Just when it's 0, I get a little nervous that people are missing that. And also, I posted a preview to Project 4. There's not a lot of content in the document. I'm at the point where my next step is to write the document, and I'll get that and then get it finalized and released to you. At least by Wednesday, I'm going to have the project finalized and released, so you have all the lecture tasks and application objectives for that. But since we're starting a new learning objective, I at least wanted you to get an idea of what the project is going to be. I'm going to give you a game, and the reason this one takes so long to develop, which has been taking a lot of my time, is I'm giving you a game, a fully functional game that you can play. The only difference, and it's very much so based on towers, which we saw last lecture. A lot of the same code. You'll see the same look and feel. The front end is almost identical. But I had to make a lot of changes to make it, something different for the assignment. And the only thing the game is lacking is the enemy AI. The enemy don't do anything. The enemy just sit there. All the enemies just sit there and do nothing. So your task for the assignment is to build their AI, and you guessed it, we're going to use data structures and algorithms to do that. So over the next 3 weeks, we're going to learn about how to represent data, and then how to work with that data. And our enemy AI is going to get a whole bunch of data. It's going to do its thing based on that data. So since we are starting a new new learning objective, the last learning objective, we're getting down to it. Let's go back to our syllabus one more time and introduce this thing. For this learning objective, there are no restrictions. You can use var, you can use val, you can use conditionals. Everything's on the table. You can use whatever you want to get the job done. For this, no more restrictions. We're done with restrictions. So at this point, you're going to be faced with some programming questions, programming problems, the lecture tasks, the application objectives, where it's up to you to decide. Do I want to use an OOP approach? Do I want to use an FP approach? Do I want to create new classes here? Do I want to use great methods that take first order functions? How do I want to do this? How do I want to approach it? Whenever you have those design questions, which will be the rest of your career also, whenever you have these design questions, it's like, okay, what approach do I want to use? Or do I not want to use either of them? Do I want to go back to the 115 days and just write a bunch of methods and call those methods? That's fine too if that's the way you want to do it. But everything's on the table, and it's to the point where I want you to start applying these concepts when they're most applicable. I don't know. It's probably a better way to say that. So the actual content that we're looking at is data structures and algorithms. We're going to look at 3 data structures in particular: a linked list, tree, and graph. Each one of these is 1 week. The schedule is pretty well segmented. 3 weeks for the objective, 3 data structures, 1 week per data structure. Sound good? So we're going to see the structure of each one of these in lecture, and then a couple of algorithms that we can use on these data structures, and you'll be expected to be able to work with each of these 3. In the homework, you're going to get references to the types of data structures that we're going to create in lecture. So we're not necessarily using Scala's built-in list anymore. We're going to use the linked list that we're going to introduce in today's lecture. That's the linked list we're going to see. Trees, there's really not a tree in the sense that we're going to show in Scala. So we're going to build one, and same with graphs. We're going to build our own graphs. And then in the homework, you're going to write methods that'll take instances of these data structures and then work with them with your own algorithms. So with that, I guess I didn't have to scroll down. With that, let's introduce linked lists and talk about what linked lists is going to be. The first lecture task is going to be on Wednesday. It's going to be to take a linked list using the structure that we have today, a linked list of players, and then find the closest player to the enemy AI. That will be the player that enemy is going to try to target and try to attack. It's going to attack the closest player to it. So with that, I want to set one thing up before we... Examples, good. Just so I have this open. Linked list. Linked list example. Perfecto. I'll set my breakpoint even. Alright, so let's introduce linked list. First, I'm going to introduce. Hold on, I'll get this. Let me reset here. All right. So let's talk about arrays. I talked about these very briefly earlier in the semester when we started talking about types and memory. So let's recall what an array is. An array is a sequential data structure. It's one continuous block of memory. And to access a particular element in an array, you start with the address of the first element. And in fact, a reference to an array is just a reference to the memory address of the first element of that array. And if we want to move to a different element of the array, we take the size of each element. So like if this is an array of doubles, the element size is going to be 64 bits. Multiply that by the index we want to reach, and then that's the memory address for that element. Since this is a continuous block of memory, and memory addresses are just numbers, we can do a little bit of arithmetic, starting with the first element, and find any element in this array that we want. The interview and quiz you'll know Wednesday at the latest. So we can use this. This is what we call random access. We can access any element of the array very quickly, very efficiently. We just do one multiplication, one addition, and we're there. This is also fixed size, so we can't resize an array because the memory address right after the end of the array might be used by another variable, might even be used by another program. We don't know what it is. It's probably it's just not memory that we can access for the array. We can't just expand an array. So if we want to expand an array, we want to make it larger, we have to create a new array, get a new block of memory with the new size that we want, and then copy everything over. So arrays cannot change size. They can't change size. They have to be a fixed size. Now, a lot of modern languages have the mechanics hidden underneath an array to do the resizing for you, so you don't have to think about it. But a vanilla, just a plain old array, cannot change size. But like JavaScript's array, they're going to hide those details from you and just let you pretend that you can resize, but it is resizing underneath the hood. So an array, I have my element at index 0. That's what I'm going to store on the heap, on the stack. And then in the heap, I'm going to go to that index and then add whatever I need to add to it to get to any other index in the array. And then after the end of the array, I don't have access to that. I'm not allowed to access that. If I try to access that, I'm going to get an index out of bounds error. Or if you're coding in C, you're just going to get whatever is stored in memory right here, which have fun with that in 220. So if you go off the end of an array, most modern languages have that feature where it's going to throw an error and say, hey, you can't do that. C just lets you do that. So Just a heads up on that. It makes things interesting, to say the least. So let's contrast that to a linked list. This is the one we actually want to talk about, but I just wanted to flash back arrays just for comparison. So a linked list, and of course, by the way, it should go without saying, but I will mention it throughout these 3 weeks. These 3 weeks of data structures and algorithms, this is a lot of stuff that is going to be explored further in 220. I'm here to lay a foundation, get you familiar with the idea of linked list trees and graphs, and arrays, I guess, that little bit that we did with arrays. In 250, you're going to go in depth into these data structures and many more. So this is kind of like a preview of 220. This is the 250. This is like the 250 flavor for these 3 weeks. So a linked list is LT2 complete in the doc. It just says TBD. No, it's not. Damn it, Priest. So a linked list is also a sequential data structure, except it's spread across memory. We're not building this in the same way that we're building an array, where all of the data for the data structure is right next to each other and localized in memory. With a linked list, the data can be all over the place. It can be anywhere in memory. Yeah, I didn't see the rest of it. It can be anywhere in memory. Each element of a linked list, which we'll end up calling a node once we formally introduce it, is going to know where the next element of the linked list lives. And fundamentally, that is a linked list. We have values spread all across memory, and each value knows how to find the next value. That's a linked list. These are variable size. If we want to add a new element to this list, we just throw it anywhere in memory. We say, hey, operating system, I need enough space to store this thing in a reference. We get that reference, we store it, and then somewhere in our list, we need a reference to that node, or that node needs a reference to the list. So if I create a new element and I say, hey, element, guess what? There's a linked list over here. There's a next value over here. Go refer to it. That element is now part of that list. Visually in memory, it looks like this. I have on my stack a reference to a linked list, which is only a reference to the first element in the linked list. So here on my in my stack, I'm going to have a variable. I named it my list here with a reference to 506. I should have my ats. I didn't realize I don't have my ats in here. These should all be ats. Those are memory addresses. So I have the elements of my list. By the way, this is the list 531. These are anywhere in memory. And I have a reference to the first value in memory. I have a reference to 506. That has the value 5. So 5 is the first value of my list. And that value has a reference to 795, which is where we can travel in the heap to find the next element of the list. Next element is 3 and has a reference to 416. 416 has the value 1. And its next is going to be null. This is how we know we've reached the end of a list. Now, I should note, normally Scala developers don't like null at all. Don't like using null at all. I'm going to use null for the linked list for 2 reasons. One, it's just a little easier. And when I'm trying to introduce a topic, I want the code to be as simplified as possible. And 2, the more important reason, because I don't really like that first reason, you're going to see this in 220 a lot. You're going to C is very keen on what we call null termination. By seeing a null and knowing that that is the end of the list or data structure or whatever, you'll see it in arrays and strings, or char stars rather, in C. Whenever you are reading data and you read a null character, that says, hey, this is the end of that data structure. So we're going to do that, use that same setup. Whenever we read a next value of null, that's the end of the list. Yeah. Speaking of just reading, sleep deprivation makes me yawn. So this is how a linked list is stored in memory. I'm going to go pretty slow through these next few slides, this slide and the next couple. Then I'll hop over to IntelliJ, hopefully reinforce what a linked list is, because there's not a whole lot to say about it. Most of what I need to talk about with linked lists are implications of the structure. So I'm going to take a while we talk about the structure here. And this is it. On the stack, you store a reference to the first element of the list, and each element stores a reference to the next element. And then once you have a reference to null, once the reference is null, that's the end of the list. So this is how we represent the list 531 as a list of ints, as a linked list. And by the way, Scala's list, the list that we've been using all semester, is a linked list. In the code, this is how it's going to look. In the repo, there's a linked list node class, and it's going to have the value. Oh, by the way, I forgot to mention. Now that you know object-oriented programming, I meant to mention this when we were in the syllabus. Now that you know object-oriented programming and functional programming, I'm just going to start using both of those casually. So just a heads up on that. Type parameter, a type parameter of A, that should be no big deal to you. You should be comfortable with type parameters at this point. So if we want a linked list of type A, what I'm going to do is use this class, and this is the entirety of my linked list class. This is what it is. We'll add some more algorithms to this. We'll add some methods to it, but this is all we need to actually have a linked list to be able to work with a linked list. So I have a linked list node. That's what we're going to call each one of those sections in memory. That's what each object is, which is going to store two values. One, the actual value of that element of the list. And two, a reference to the next node, which is of the same type as this node. So if we want a linked list of type int, we're going to create a linked list node of type int. So A is int in this case. Give it a value, which has to match the type parameter, which is int. And since this, when we first create it, this is going to be a list that only contains one element, I'm going to say null next is null. So this is just a one element list. Notice that these will be mutable lists. Does it feel weird to you? It feels weird to me that we're seeing var again. We're also going to see conditionals. We have our full force, our full arsenal of programming knowledge available to us. You don't see a repo in the doc? It's because there's no repo in the doc. I have the repo. It's just, I know if I put it in the doc in the preview, some of you are going to clone it right away, which is perfectly fine. But then when I update the repo and finalize it, some of you are not going to pull the updates. And it's just going to cause so many issues and headaches. I don't want to deal with them. You don't want to deal with them. So I'm not going to release the repo until it's in the state that it's going to be in for the actual release. Because if I got to change like one method, then you submit to Autolab, you're going to get nothing but errors. You know, I just don't want to go through those headaches. I've been through them before. I made that mistake before. So we have this linked list node. We're going to create a new linked list node. And at this point, my list is going to be a reference to a linked list node, which stores the value 1 and has next of null. So we would say my list is a reference to the list that just has the value 1. Now I'm going to reassign. Again, does it feel weird to reassign? We have our power back. My list, we're going to reassign to a new reference for a new linked list node that we're going to create containing the value 3. And next is going to be a reference to my list, the list that we created on this first line. So now my list is reassigned to a list that has the value 3 and a next of a node with a value 1, which has a next of the value null. So now my list stores the list 3, 1. And we're going to do this one more time. Create a new linked list node of 5, the value 5. My list is going to be this node that was created, containing the value 3 and then 1. reassign that to my list, and now my list is storing a reference to the list 531, and we've successfully created the list that we visualized on the previous slide. We have on the stack, my list is referring to a node that has the value 5 and some reference to another linked list node containing the value 3, which has a reference to another linked list node containing the value 1, which has a next of null, indicating the end of the list. Let's walk through this. So this linked list, let's walk through this again. I'm going to walk through this like 3 times, by the way, because this is the most important part, just getting a feel for the structure of a linked list. Because moving forward, the rest of the slides, the rest of the week, I'm just going to assume you know this. I'm just going to fly through a whole bunch of cool stuff. Cool implications. I think they're cool. Cool implications of this. So we're going to create a new linked list node. We have the keyword new. That means we're creating a new object on the heap. We're going to create a new object on the heap. I'm going to give it a reference. And here I have my ats. I don't know why I don't have them in the previous time that I do it. That I show the heap. Blame Jesse for allowing it. Are they picking on you, priest? Yeah, and Ren. You blame Ren too. You can just blame everybody. With the value, so I create that linked list node. Value is 1. Value. Oh, I shouldn't have named that value. Value, variable name value, a state variable name value with a value of 1, and a state variable name next with a value of null. Value and next. On the next line, my list is going to resolve to the reference to this object on the heap. So my list is storing a reference. At that point, my list is storing a reference at 416. This object on the heap, when we create this new linked list node, that's a new object on the heap with a value 3 and a next of 416, what my list used to refer to. And then we're reassigning my list to the return value of this constructor, which returns a reference to the object that was created, which in our case here is this made up number 795. It is a real number, but I just picked that one randomly-ish. Now my list stores a reference to at 795. That's what my list right here resolves to. So we're going to create a new linked list node with 5 and 795. Get a new reference somewhere in memory, we don't care where. But we have a reference where how we can find that object. And now this returns that reference, and my list is going to be reassigned to that reference 506. And now that's what our list is. What's stored on the stack in this variable isn't, we refer to it as just a list. My list stores a reference to a list. We like to think of it that way, but really what it stores is a reference to a linked list node, which has a value and a reference to the next linked list node, which stores a reference to the next linked list node, which stores a reference to null. Yeah, basically we're making a list and then creating methods to do stuff with lists. Yep, exactly. So this is a linked list. This is how linked lists work, by the way. This isn't just something I'm showing you because it's an academic thing to show you. This is how linked lists in Scala work. When you use the list class, this is what it does. That is a linked list. It is a linked list. And then we're going to see how Scala gets things done with that linked list. It'll be a little different because Scala's linked list is immutable and ours is going to be mutable. So we have a little bit of difference there. We can actually make changes to our list. But the Scala linked list, we actually can't do that. And I'll explain some of the implications of that. Who censored you? Oh, yeah, because I didn't say, because I said stuff instead of the other word. Okay, is everyone good on the structure of lists? Are linked lists only used when you have a type parameter, or are all linked lists lists? So with all your data structures, any data structure that's worth its salt is going to take a type parameter, because you want a data structure storing whatever you want it to store. Like you wouldn't want a linked list node int without a type parameter that can only store ints. If I wrote a linked list class that can only ever store ints, that's just way too restrictive. It's a kind of useless data structure, because as soon as I want to store doubles, I want a list of doubles in my code, I can't use that. I can't reuse that code anymore. So we like the type parameters because that lets us write one data structure that can store literally any type. Not all at the same time, but creating, whenever you create a list, you want to create a list of strings or a list of players or a list of dynamic objects or game objects. You want to create lists of different things. So that's why we take a type parameter. We take a type parameter so we can say, just give me something. Give me some A's. I'll store A's for you. In this example, we're going to set A to int and create a linked list node of int. In Scala, using Scala's list, you would create a list of type int and then create a list and give it some ints. You would create a list of strings, give it some strings. We take the type parameter so this data structure can store whatever the user, whatever anybody using this linked list wants to store. Yeah, you can name a type. You can name your type parameter priest if you want. Yeah, it's a standard to have these as single character names, but that's not a requirement by the language. You want to name those priest? Go for it. Just don't do it out in industry, because you'll get made fun of in the code reviews, but I think you're kind of used to that anyway. I mean, things like this is how you bring it upon, bring that on yourself. But that's entertaining. So if you want to entertain your coworkers and yourself. all right, let's keep moving. It's toxic. I'll eat a priest. Priest likes it. Right? If you ever want me to stop and shut everybody else down, I'll do it. But I don't know. I think the back and forth is entertaining. No, yeah, exactly. Yeah, I'm good. Yeah. Yeah, if you ever want to stop, just say the word, it'll stop. So we have this linked list structure, and now it's on to the implications. Like, what do we do with this? How do we work with this? And these are all algorithms that we're going to see today. How do we find the size of a list? How do we print all the elements of a list? How do we access an element by its location? How do we how do we add and remove elements, and how do we find a specific value? These are all the things we want to talk about today. So let's start with two quick ones, and then we'll head over to IntelliJ for a little breather, for a little digestion. First, the size of a linked list. And by the way, I'm going to show all these recursively. I'm going to use recursion throughout all of the next 2 weeks. You're going to see recursion after recursion after recursion. So with size, I'm going to write a recursive method. This is called on a linked list node. This is in the linked list node class. So a linked list node, the size of the list referred to by a linked list node, is going to be either 1 if next is null. So either this is a list of size 1 and the size is 1. Because next is null, it's just the element referred to by that linked list node. That's it. That's the whole list. Or it's the size of the next element. So if next is not null, then there must be a linked list node stored in next. Well, I'm going to ask that node for its size. And when it returns its size, I'm going to add 1 to it and return that. So if this is a list that's longer than 1 length, I'm just going to ask the next node, hey, what's your size? I'm going to add 1 to it and then return that. Done. That's our size method. So now if we call this on the head, the first element of a list, which we call the head of the list, it's going to ask the next element, hey, what's your size? It's going to ask that the next element, what's your size? That element's going to ask the next element, what's your size? What's your size? All the way down until we get to the last element of the linked list. Last element's going to be like, I got the answer. I know this one. I know it. It's 1. It's going to say, yo, my size is 1. Second to last element's going to be like, oh, good, your size is 1. Well, my size must be 2. The third to last element's going to be like, oh, your size is 2. Well, my size must be 3. Next one's going to be like, oh, your size is 3. Mine must be 4. I must refer to 4 elements. And so on until we get to the head of the list, which is going to return whatever the actual size of that list is. Two-string. Neat. It is neat. So two-string, similar. We're going to use recursion. If we're the last node in the list, we're just going to return our value as a string. If I'm a list of just one element, return that element as a string. Done. If I'm not the last element, if a node is not the last element in the list, we're going to recursively call toString on the next element, get the entire rest of the list as a string. I'm going to splice in my comma, and then call my values toString, and then return that. This is one case where recursion really cleans up your code. If you don't use recursion, use a loop for this. Getting these commas just right can be a little bit of a pain. You got to have a conditional in there to say if this is the last element, don't add a comma after this. But if it's not the last element, add a comma after it. You got to do some logic like that. With recursion, we already have that conditional built into the recursion. Just don't add the comma here, but do add the comma in the recursive case. This is a case where recursion just, I don't know, just nice and clean. I think this is a nice, clean method. And once you know how to read recursion, it's pretty readable. It's very legible, too. If you can't read recursion, if you're not quick with reading recursion yet, it might take a little bit to read this. But once you can read recursion, okay, the base case is going to return it as a string. The recursive case is going to make the recursive call, and then concatenate its element before it with a comma. Cool. So let's take a little field trip into IntelliJ. Stop whatever server's running. And I want to run this program, the program that we saw before. Oh, let me show you the linked list node, by the way. So our linked list node, this is what we started with. Oh, yeah, I should mention this note. This is a simplified, this is just meant for educational purposes. We actually can't represent the empty list with this linked list node class. Just so you know. We can create a linked list class which stores a reference to a linked list node, which I'll probably have to do. I'll probably have to set up for the homework at least, and then we'll talk about that on Friday if I do. So this is our linked list node class, or I'll just say it won't be the empty list. So this is the linked list node class. Here's our do I have the regular size in here? I only have the tail recursive version. Anyway, here's our size method. It's a little bit different than what you saw. I can explain this after lecture if somebody's interested in another recursion example. I wanted to use tail recursion here. And then the toString, which will be unaltered. Along with a lot of other methods, some of which we'll see today, some of which we won't. But what I want to show is constructing that list and then working with it a little bit and seeing how this all behaves in memory. And I want to make sure I do this because I feel like I haven't done enough debugging examples. And when I mention the debugger in office hours, a lot of you are confused as to what I'm talking about. Maybe not what I'm talking about, but how to use it. And also how to generate stack and heap examples. Like when you're studying for a quiz, and you know that I'm going to ask about the stack and heap on that quiz, being able to study for that thing when I'm getting pretty light on the lecture examples in the slides where I draw out the whole stack and heap. The debugger, the intent is that you use the debugger to generate infinite examples and infinite cases where you can see that. So let's take a look at this. Let's step through this program. We hit our very first line. I'm going to step. We're going to create a new linked list node where this is a reference to the node that's being created. At 817 happens to be the reference that we got here. Assign those two state variables, 1 and null. And then my list is going to be a reference 817 that we just created with the value 1 and next is equal to null. Now when we create the next linked list node, my list is a reference to this list at 817. And whenever you see a reference like this, like there's no section in the debugger that says here's everything that's on the heap. But whenever you have a value and you see this at and then some number, that means it's a reference to an object on the heap. So if you look through your whole stack and you find all of the references, that's going to tell you everything that's on the heap. So this at 817 and 3 are going to be our constructor parameters. So this value is going to be 3. Next is going to be that linked list node at 817. It has the value 1 and a next of null. And that's what this linked list node is going to store. This is going to be at 823. That's what we rolled for our reference. Then after that's done, my list is going to be a reference. That reference at 823, which has a value 3, a next of at 817, that object with a value of 1 and a next of null. We step through one more time. We're going to go to this constructor, return. And now my list is a reference at 831, the new one we just got from this call to the constructor of the linked list node. 5. Next is 823, which has a value 3 and a next of 817, which has a value 1 and a next of null. So that's the end of the list. Yeah, I want to do some sort of chat during live lectures. Like even when I'm busy lecturing and not interacting, just that y'all can interact with each other is extremely valuable. And then like something like my list dot next dot value, that should have printed out 1 if we follow the chain here. So if we go to our console, we got 1 on the console. We didn't talk about prepend, so I won't get into those too much. But one thing you can see in the debugger is it is actually showing like 531 here. What it shows right here is the toString of that object. So this object's toString has been overridden with this. So to get this string right here displayed in the debugger, it's going to take this object, call toString on it, which is going to be this recursive call, to be able to get that printed to the screen. Where's my mouse? That was your debugging demo. All right, so let's go through a few more. Ooh, a little low on time. But let's go through a few now that we're comfortable with the structure of a linked list. Hopefully that solidified it at least a little bit. Now let's go through some of these algorithms, which will go pretty quick. I want to spend the bulk of today's lecture on the structure of a linked list, and then we can rip through the algorithms pretty quickly. So accessing an element by location, we have the location of an element, and we want to retrieve that element from the list. This is commonly the .apply method, or what a lot of you have been doing this semester is removing the apply and just doing in parentheses the element. For ours, we're gonna use the apply method for our linked list node and say .apply of some number, give me the value at that position, or if this were an array, that would be the index. Give me the value at this index. But it's not index here because we're having a linked list. And I've mentioned many times that this is a very, very slow operation. It's very slow to access an element from a linked list. And hopefully by now you can see why that's going to be so slow. So if we want to do apply of 4, or give me the the 5th element of this linked list, this is the same as saying this dot next, dot next, dot next, dot next. Whatever number we have here, that's how many nexts we're going to access. In the code, if I is equal to 0, well, that means you want this element. So we're going to return that node, and we're returning a reference to the node, not just the value at that index. We're going to assume we want the full reference to a node, which is something common we'll do with linked lists. You'll see why when we get into insert and delete. So we're going to return a reference to that node, and then if we want the value, we would do dot value on it. Else, we're going to call next once. We're going to use up one of those next calls that we have to do, and then call apply on that node with I minus 1. We've called next once. The next node has to now call next I minus 1 times. So this is a linear runtime algorithm. We have to call dot apply this many times, however, whatever n is for our call. Very, very slow. If we want to get the last element of a million element list, we have to call dot next a million times. This is much different from an array, where an array you have an array of a million elements and you want to get the millionth element. It's still just a multiplication and addition, and then access that memory address. That's a constant time operation. This is a linear time operation. Very, very slow. Very, very slow to get a specific element of a linked list, because you have to jump all around memory. If you have a million elements all randomly scattered throughout the heap, and each one only knows where the next one is, you have to travel to every single node. You have to bounce all around memory, follow the entire chain, follow all the links of the chain, you get the terminology, and get to the end of the chain, and then be able to return that to your program. How do we add an element? So to add an element, we're going to need a reference to the node right before it. So let's say we want to add 2 right after 3. We're going to need a reference to this node, and then we're going to update the reference of this node, and set the reference of the new node. So if I want to add a node right here, what I have to do is take this reference, which is why our find and all of our other methods are going to return a reference to a linked list node, because if we want to add or delete, we're going to need a reference to a node. We don't just want the value 3, we want the entire node. So if we want to find this and then work with that node, we need the reference to the whole node. So we'll have a reference to this node. We're going to create a brand new linked list node with the value that we want. We're going to set next of that node equal to whatever next of this node was referring to. This node was referring to this node, so we're going to need this reference from next and store that in this reference next. And then we have to update next of this node to refer to the new node that we just added. So a decent amount of work going on. We're creating a new node and we're updating a couple of references. In the code, we can do this really compact. We're creating a new node. We're giving it the element that we want to insert. And this is a method of the linked list node class. So this is called from a specific node. We're giving it the element that we want to add. And then the node that we're adding after this. Yeah, it's rain in the background. I should have closed the windows before lecture. So it'd be a little quieter. So this node, whatever it used to refer to, the new element, the new node is going to refer to that. And then this node's next is going to refer to the new node that was just added. Very soothing. Yeah, I like it. Maybe I'll do that on purpose next time. To delete an element, we need a reference to the node right before it. So let's say we made a mistake. We didn't want to add that to. We're going to remove it from the list. We need a reference to the node before it. And this is even simpler than adding. We're just going to update next to bypass that node. We just update next and just cut that node out of the list. We say, hey, node that I'm deleting, what's your next? Well, that's my next now. Cutting you out of the whole chain. Now, this node still exists, but it's likely to just get garbage collected. We don't have a reference to it anymore. It's effectively not part of the list. We don't care that it refers to this node anymore because we don't have a reference to it. Or maybe somewhere else in our code we have a reference to it. It's whatever. And that's even simpler than adding this.next equals this.next.next. Cuts that this.next, what it used to be, cuts it completely out of the list, and it's gone. To find a value, say we want to find a specific value based on equal equal. In a linked list node, we're going to check if this dot value, if the value at this node is equal to the value that I'm trying to find, then return a reference to this node. This node contains the value that we want. We're good. Let's just return that. So this will return, by the way, the first occurrence of that element. Else, we're at the end of the list. If we're at the end of the list, then return null, and we're going to use null to signify that that element does not exist in this list, that we just haven't found it, doesn't exist. Else, make the recursive call. So we have two base cases here. Either we found the element, we've reached the end of the list without finding the element, or we're making a recursive call and just saying, hey, I'm not the end of the list and I don't have this element. Hey, .next, you got this? You got this element? And then it might make a recursive call and so forth. This could be written recursively or iteratively. This is one of the few times where I'll show an example. I think this is the only iteration that I show this week. Actually, for the next 2 weeks. So we could do this with the usual loop. We're going to start with this node, the head of a linked list. We're going to iterate until the next node is either null or we found the value that we're looking for, and then we're going to update node to be the next node. So you could argue that, there's certainly a debate to be had here which one is the preferred way. It's a matter of taste, I think, at this point. But you could do it either way here. And then for each, we have a function that we want to call on each element of the list. We take this function, which takes an element of the type of the list and returns unit. The whole thing returns unit. We're going to call the function, and then if we're not at the end of the list, recursively call for each with the same function, so the next node can call f on its value. Recursion is looking mighty clean. And one more map. Oh, we're a little over, but let me just finish these slides so we don't have to go back on Wednesday. Map, we want to create a new linked list with all of the elements in the original list, but with a function applied to it. This is how that looked with Scala's built-in list. It's a mutable list. We create a list of ints. We got a bunch of ints. We call .map. We give it a function. We get a new list with all the elements of the original list with this function applied to it. Is kind of the terminology I use. I use that terminology in the handout for genetic algorithm. It's hard to use other terminology because I always want to just say map. Oh, it maps this list using that function is how I want to say it. I can't really say it like that when I'm explaining what map is. But that's hopefully making sense to you now when I say with that function applied to it. We get all the squares of these methods, or of these elements, because we gave it the square function. In our linked list node, how would we make that happen? We want to use that same syntax, give it a function, call map with a function. So map is going to take a function f. It's going to return a new linked list node. We're going to compute the new value that we want to add to the list that we're returning by calling the function on the value at this node. And then we're going to create a new linked list node, which is kind of a duplicate of the structure of this node, with the new value instead of the old value, instead of this dot value, where if we're at the end of the list, next is going to be null. And if we're not at the end of the list, next is going to be a recursive call to map on the next node. So this is going to return a new linked list node with everything after this element having the new list with map applied to it, the function for map applied to it. Then we're going to create a new linked list node with our new value with the next of the rest of the list. Something I didn't show in functional programming, but we can actually change types of map. We did see changing types of map just using this, but 2 type parameters is what I didn't show. So the linked list node class has a type parameter A. We can actually have a method that takes a different type parameter, and this is if we want to call map with a function that changes the type of the list. If we want to change the type from A to B, we give it a function from A to B, take another type parameter, return a linked list node of B, and then everything else is the same as our original map function, map method.